All right, let's continue with what we were starting to talk about the last time, namely the frequency dependence of polarization mechanisms and thus the frequency dependence of the dielectric constant as well as the losses that are associated. And I briefly gave you an overview that because of the nature, when we're looking at all that we've looked at so far is in terms of DC, static conditions, as soon as you are using AC and start increasing the frequency of the current, the applied voltage, you suddenly start seeing one by one different mechanisms unable to respond at higher and higher frequencies, and so they drop out of the picture. So we'll have to look at it in terms of each polarization mechanism versus frequency. At what frequency, up to what frequency can it sustain, and beyond that it is ineffective. Now we have one of the other reasons that affects, one is of course the frequency response of the polarization mechanism that affects the AC response. And there is a second factor too, namely thermal agitation. We see every time the field flips and the particular dipole is wanting to orient itself against, in direction with that field, it goes on doing that. There is at the same time also a thermal energy being given to the system at any given temperature that is seeking to randomize it and interferes with this flipping back and forth. So you're going to get losses. And it is these two things that are responsible then for the different mechanisms being responsible at different frequencies. So what we are interested in is to know the alpha versus omega, omega being the frequency and alpha are polarizability. That's what we are interested to know. And once we know alpha, we then know epsilon r versus omega, and so on. Well, if you look at it in the AC conditions, omega r no longer turns out to be simple omega r. We have to write it then as a complex number. Not omega r, what did I say? Epsilon r. Epsilon r is not a dielectric constant, whatever it is epsilon r dash minus j epsilon r double dash. Now we are expressing it as a complex number to account for the, there are two things there. This part here, this epsilon r dash, that's the real part of it. And it is this epsilon r dash that we make use of when we are calculating, for example, capacitance values and things like that. When we want to make a calculation of what is the capacitance, say in the parallel plate capacitor, epsilon r, epsilon naught, A by D, what we do is to make use of this real part of that equation. And when you look at it in terms of frequency, it decreases with increasing frequency overall. In addition to that, you've got this now, the second term there, epsilon r double dash, which is the imaginary component. And what it represents is the loss in the dielectric medium. And when we look at epsilon r double dash, the loss, as a function of omega, we see peaks appear at specific values of omega. And at other frequencies, it's practically zero. It builds up to a peak, and then you've got zero values around it. This peak is also known, these peaks particularly for each mechanism are known as relaxation peaks. And it is at these frequencies that the loss is a maximum. Okay? So the omega r dash gives you the real component, which is more or less like what we've been writing as epsilon r in all our equations. So when we come across it again, we are going to make use of the real part in our calculations. And epsilon r double dash is what is representing the loss that is there in this medium. What we really want to do is to make this, we want to minimize it as low as possible for any given value of epsilon r dash. That's normally what we're trying to do. I'm trying to store charge when epsilon r double dash is the loss component of it, then I want to minimize it for any given r epsilon r dash. And so a quantity is defined called tan delta, which is epsilon r double dash by epsilon r dash. The loss, the imaginary part by the real part, and it is known as, tan delta is known as the loss tangent or the loss factor. And the smaller it is, the lower are the losses. So these ideas in general are applying to each of the different mechanisms that we saw, namely electronic, ionic, interfacial and orientational, and they contribute at different frequencies. So if you plot now the real and the imaginary components, both of those as a function of frequency, this is what we will see. What we are plotting is each of them individually, epsilon r prime and epsilon r double prime. You'll see something like this, a series, oops. And at different frequencies, roughly I'm putting it there, in hertz. Okay, it's not on any real scale. I'm just putting numbers corresponding to roughly where, at what frequencies these things behave. You may wonder, oh, the scale doesn't look very proper there. But these are the rough numbers at which the different mechanisms are operative. You might guess from looking at this that this part is due to what? Which polarization mechanism? Which one sustains to the highest frequencies, I said? Electronic polarization. All right? Then it eventually tapers down to 1, this the real part of it. Okay? So the electronic one can sustain to the highest frequencies and contributes to the polarization at high frequencies. What about this one? That's ionic. And then we've got orientational or dipolar. And then we have interfacial. Very good. Interfacial or space charge, because it is like charge is stored in space, much like we use the term space charge layer when we were talking of semiconductors. The same concept, that's why it's also known as space charge. So this is how the distribution looks for epsilon r dash or epsilon r prime, the real part of it. 12. I'm sorry, oh, it's the same. It's 10 to the power 16. And when we look at these frequencies, where they lie, somewhere here in this range, we are talking of radio frequencies. Okay? Those are radio frequencies. And where the ionic part is lying is about infrared. And up here, we are talking of UV. The kinds of energies that are involved, obviously, depends on the frequency. So UV, IR, radio frequencies, that's roughly where these frequencies lie. Now in the same plot, we can also plot the epsilon r double prime, which is the loss component. And what is seen is that very close to these drops there, we get peaks like this. So what we're plotting here on the same plot, excuse me, is epsilon r double prime. And around these values, we will get peaks, and then they drop off. Okay? So the losses are maximum for each of these at some particular frequency over here. Dielectric loss, which we have been dealing with in terms of the tan delta, the total losses, are sensitive to, as we may guess, frequency. If the frequency is different, depending on that, we will get different losses. You can see overall the whole dielectric, the constant is decreasing with increasing frequency. We would expect it to be sensitive to the applied field and to tan delta, which is more or less a material parameter. These two are external, frequency of applied, the applied frequency, and then that's the field that is applied. And this is something that is more of a material parameter. Okay? So if we write an expression W volume, which is the power dissipated per unit volume, it can be expressed as epsilon naught epsilon r prime omega the field squared tan delta. The same parameters that I've mentioned, namely this, this, and this. Okay. So this is some, from looking at this we can say that the higher the frequency, the higher the loss, the larger the field, the higher the loss, the larger is tan delta, as might be expected from its name, namely loss tangent, the higher the loss that is expected. So this is just a quick thing about the frequency dependence that we have for the different mechanisms. One more thing I'd like to touch in passing almost is what I mentioned at the beginning, that dielectrics are used not only for storing charge but also in terms of insulators. So the property of interest there would be what? Pardon? Yeah, if I'm worried about using it as an insulator, which property of the dielectric is important? Well, kind of. It's insulator, so it's not conducting. Breakdown. I mentioned it the first time, right? What we're interested in is the breakdown field or what is also known as dielectric strength. Okay. We are going to use this as an insulator between two plates or in some form, and we want to see what kind of field can it sustain across itself before it eventually fails. And there are different mechanisms by which it fails, and we will look briefly at these. I don't have time to go into details. So initially it is storing the charge and it is preventing, it's acting like an insulator basically between these two. Field goes on increasing, eventually we get breakdown at some voltage. And that voltage that field that is there, the breakdown field, is known as the dielectric strength or the breakdown field of that material. That value of the field that it can sustain before it breaks down and current starts passing through it. Okay? Now, it turns out that in gases and liquids, if I go on increasing the voltage and breakdown occurs finally, the field has gone so high, what would happen or what would you expect when I reverse it so that now, okay, breakdown has occurred and I now turn down the field. I reduce the voltage and the field decreases. Will it still function as a capacitor, for example, or as an insulator? What would you expect? Why?
Because of the reverse alignment of
Well, it will depend on how it broke. I mean, what caused the breakage? That's primarily the mechanisms. If we understand, we can answer that. I'm just tossing it to you as a question to see if there's any ideas out there. Turns out it is reversible. So breakdown in gases and liquids is reversible. But in solids, it typically is not reversible. Because what ends up happening during breakdown in a solid is that some kind of a permanent conducting path is set up, and once that is there, even if you reduce the voltage, it's going to conduct through that path. Okay? So in solids, once it's failed, it's failed. But if you're using gases or liquids, you can turn down the voltage and thereby use it again. Now, what are the factors that influence the breakdown field? And we'll look at a few. I won't go into details. Here are some of them. I'll list primarily, and occasionally I'll discuss one or two. The molecular structure of the material itself. What kind of bonding we may expect could play a role, whether or not it fails catastrophically. What kind of impurities may be there? Okay? If there's certain impurities that can result in charge transport, then once you have high enough field, those impurities, certain ions may be there or certain metallic impurities, they start conducting current actually. And so much earlier than you would expect for a purer material, we see failure. So that's a possibility. Microstructural defects is the next one, where in particular I'm thinking of voids, micro voids that may be there. Remember, inside a void you've got like air. So even though some kind of internal breakdown can take place in these voids, as across two parts of the void the discharge is occurring. Now it will also depend in particular upon sample geometry. What kind of shape the sample is in, pointed shapes, tips, corners, various things can influence when it will break down. Excuse me. The nature of the electrodes, whether those will begin to influence whether charge gets transported across, whether they will get damaged at the high fields. So many things could happen with the very electrodes that we are using to attach. Then environmental conditions like temperature. Up to what temperature can it sustain? Beyond that, the material is getting weakened, maybe it will fail. We may guess humidity. We can guess that if I've got moisture in the sample or across the surface of the sample, current can flow through that and short out the capacitor itself. That's a thing. In our beautiful place here, dust. Form a nice film of dust which has got enough of material in it to conduct. That's a very common failure that occurs here. Aging. The material itself is deteriorating with time. Its properties are changing, and gradually with it, as it grows older, we may say, the bones are getting weaker, the teeth are falling out. That's what happens in human beings. Dielectrics also age. And then it will also depend to some extent on the duration of the applied field. How long did it endure a particular field? It may be able to sustain a very high field for a very short period of time, but if you apply the same field for a very long period of time, it could lead to failure. And as we saw earlier, depending on the particular mechanisms that are operative, frequency could also play a role. Duration and frequency of applied field. These are different types of factors that could play a role in shaping the breakdown field. I'm going to list a few examples just to give us a feel for where all we find these phenomena. So here we have, say, a material breakdown voltage or breakdown field, and maybe some comments or remarks of the particular specification. So air, for example, or atmosphere. When we deal with this, we are talking at some atmospheric pressure, 1 atmosphere pressure. It has got a breakdown field in units of kilovolt per centimeter. It's 31.7. I should be careful. There's some that are megavolts also. All right, I'll write the unit separately. 31.7 kilovolts per centimeter, and the frequency is specified as 60 hertz. And this is discharge across a 1 centimeter gap. Already you have to give some conditions. If you try to reproduce it, it may be different in other cases. Now, if you've ever done electrical measurements, like you're trying to do some measurements in air, you're measuring current versus voltage or something, resistivity, you'll find that as you increase the voltage, that means you're increasing the field, eventually breakdown occurs while you're measuring. And so sometimes to avoid that, because you want to test that material to higher and higher voltages, because the material itself has not broken down, it's the air between the electrodes or the probes that you're using that has broken down already. So what they do sometimes is to use this gas SF6. You fill the chamber with SF6 and then you do your measurements, because SF6 can sustain higher voltages before it will break down compared with air. So in this case, it can go up to 79.3 kilovolts per centimeter at the same frequency of 60 hertz. And thereby it is used in various applications, like I said, measurement, or in high voltage circuit breakers. Because as you see, when you pull out even a fuse, there's a spark across it. That's basically breakdown of the air, right? Momentarily, that happens. Now, when you're dealing with high voltage things, those sparks could carry quite a bit of punch in it, and it can destroy things. So if inside that, you can seal it off with SF6. Then the air, instead of air breaking down, you've got SF6, and it can sustain a higher voltage. Here's a polymeric material, polybutene, which is a liquid, and it can sustain to greater than 138 kilovolts per centimeter at 60 hertz. So as a liquid, it's got some interesting applications like filling up the high voltage cables. You've got the actual cable, and then you've got insulation in between, I mean the outer covering, and you can use this as a liquid filler in between in high voltage cables. Transformer oil, this is another important one. You've seen all these big transformers around the place, there's oil in it, and to prevent the breakdown and sparking between those. Transformer oil is good up to about 128 kilovolt centimeter inverse at 60 hertz. And then some other, the not so common one, amorphous SiO2, which is used in circuitry. We saw we are putting in, say, MOS devices, you've got an oxide layer. So that oxide that we have, which is amorphous, can actually do something much higher. We are now in megavolts.
So what is Piezo?
You know, I'm not sure what transformer oil is. I really don't know. I have to look that up if I have to answer that question, but I don't know. 10 megavolts per centimeter inverse under DC conditions. Okay, so it's can do it to very high voltages. But the assumption here that we're talking about is that first of all we're talking of rather thin film and no defects. So your actual MOS, oxide film may actually sustain lower voltages. This is sort of the upper limit, assuming there's no defects and it's a nice thin film, smooth film. One final one, say borosilicate glass. I'm giving these so you can get a feel for the range of properties of different kinds. Here we see the influence of the duration of the pulse. Field of 10 megavolt per centimeter for 10 microseconds. So for a period of 10 microseconds, it can sustain 10 megavolts centimeter. But if you increase the duration to 30 seconds, I think it was seconds, 6 megavolt centimeter inverse, it will fail.
What is the application of such a time boundary?
Where temporarily it can sustain. As long as, that means normally in normal usage, it can protect up to 6 megavolt centimeter inverse. So this is sort of built in. As long as my field doesn't exceed 6 megavolts for more than, or 5 to be on the safe side, for more than 10 microseconds, momentarily it may spike. Voltages go spiking in your, in our homes and in, so your PC is, you're protecting it with a UPS and all that. Momentarily it surges. As long as it surges for a very short duration, you can prevent breakdown of that material. And the higher voltage that it can sustain, albeit for a very short time, that is really related to an intrinsic breakdown. We will see some of this in a second. And this lower field that it will sustain is due to thermal breakdown. I'll come to that in a second. What are these? Numbers I'm just giving you, don't have to memorize anything, that's not the point of it, but just to get a feel for in various areas how these are playing a role. I mentioned breakdown mechanisms, intrinsic and thermal. And when we talk of intrinsic breakdown, what we are referring to is something similar to our idea of avalanche breakdown that we saw where? Diodes, right? That is basically impact ionization. One ionizes two and then it goes on and then it's out of control, avalanche what we saw. So impact ionization, and that's why it's intrinsic. It has nothing to do with it overheating or something like that. Beyond that, it just cannot sustain. On the other hand, thermal breakdown, as the name implies, is it's getting too hot. Okay, so eventually the material is getting too hot and the heat effects are important there. Another one may be electromechanical. You see, if you remember, we had our dielectric between two plates. Okay, and when we have these surface charges that are there, plus Q and minus Q, When the field is high enough and this dielectric is thin, what's going to happen to it? I've got a positive charge here, I've got a negative charge here. It's going to attract each other. In other words, it's going to squish this thing. It's going to push it together. So we're talking of compressive stresses that are being generated in the material because the two electrodes, when they are attracted together at high fields, are pushing each other. And that could lead to stress leading to deformation and other failure defects being generated and other kinds of fracture or various things that could happen. That's why it's called electromechanical type of breakdown. Or you may get internal discharges. I mentioned that briefly when we were talking about microvoids, that when you have voids and pores or cracks, some discharge may occur inside it, and that's it's going to be pretty hot there. That'll burn a little more and then crack a little more and so on, and eventually you get failure. You could also have some external discharges that could cause failure, and this is dependent on conditions like dust, humidity, and so on. Aging, as I said earlier, could also result in a weakening of the structure, leading to premature failure due to breakdown. Okay, I wanted to discuss capacitor dielectric materials. I think what I'll do is I have a more important thing I want to touch upon, and then I'll come back to these capacitor dielectrics, the kinds of materials that are used and the types of capacitors that are available which make use of these dielectric materials. But before that, because I really want to just briefly discuss what is piezoelectricity, ferroelectricity, and pyroelectricity, which is another important class of materials that are used. What I'll do is I'll jump to that, and then if time permits, I'll come back and discuss the various kinds of materials that are used in capacitors. Okay, so we'll just jump over to piezoelectricity to start with. There are some crystals, say quartz, which is crystalline SiO2, or barium titanate. When you put pressure on them, they develop some voltage across the faces, crystal faces. So the application of pressure to the crystal results in a voltage that is generated. So you press it and you get voltage. You release the pressure, the voltage is gone. This effect, that you can apply a force and get voltage across the crystal faces, is known as the piezoelectric effect. And fundamentally, it's because that when you press it, you're applying the forces, you're causing a shift in the dipoles, the charges, and so you develop polarization, and then that results in the formation of surface charges building up, leading to a voltage across this. That's the basic idea. We won't go in great depth. But it's a very interesting effect that finds a lot of useful applications. And we see that these are insulating or dielectric or ceramic materials that exhibit these properties. You can also have the opposite effect, inverse piezoelectric effect. Namely, that if you apply some field across this, it will change its dimensions. It will either expand or contract. So very useful. You can imagine, basically what it's doing is converting electrical energy to mechanical energy, or mechanical energy to electrical energy, one way or the other, depending on what you're doing. Excuse me. So piezoelectric converts our pressure or force to a voltage. In this case, we apply a voltage, we get strain, maybe, or change in shape. That's the basic idea. And in a series of sketches, I'll try to illustrate, basically. If you've got a piezoelectric material with two electrodes on it, as long as there's no voltage applied, there's no polarization, nothing is happening, it's okay. But when we apply some force to it, we see that across this now, we get, we've pushed it together, and so we will get a voltage being generated across that. And the opposite effect is you apply this field and you see the change of shape. You switch the direction of the field, the shape change is opposite. Very useful. So I applied, say that this face and this was positively charged and this was negatively charged. If it changed, if it expanded, when you flip the voltage, it will contract. The dimension will change. So you can think of all kinds of interesting applications for this effect. It turns out that not all crystals can demonstrate piezoelectricity, and there is some logic to what some kind of a rule as to what kind of crystals can show piezoelectricity. The kinds of crystals that can show piezoelectricity are called non-centrosymmetric crystals. So what is centrosymmetry? That's the question. If you want piezoelectric, we want non-centrosymmetric crystals. So what is centrosymmetry? You may guess from the name that centrosymmetry implies that the crystal has a center of symmetry. That's why it's called centrosymmetric. I don't know what's your background in crystallography, but very briefly, very quickly, I'll illustrate the idea of the center of symmetry. Take, for example, some material like sodium chloride. It's got a cubic unit cell. And in the absence of any force, it may look something like this, in just drawing it in 2 dimensions. And when we look at this crystal, what we see is that from the, say from any point actually, but let's take the center here, origin. If I draw a line to any one of these, a vector, let's say in this direction, and if I draw a vector in the opposite direction, I'll get the same ion. So if this was sodium, in the opposite direction, through that center of symmetry, if I go, I get the same ion. Okay, for any of these you can see that's true. And this is, I'm drawing it in 2D, but the picture is true in 3D. If you think of a cube, you're drawing body diagonals, for example. You're going from the center to one corner, and if you go to the opposite corner, you'll find the same kind of ion. If you look across 2 faces, the same thing is true. So that is known as a center of symmetry or an inversion center. You're inverting across that center of symmetry. And it is seen that in the absence of force in a crystal like this, what we have is that the centers of positive charge and negative charge coincide. Okay? So there's no dipole, no net dipole. And what would happen to such a crystal which has no center of symmetry if we apply a force, let's say, in pushing it like this? When we apply a force, all we do is move everything a little closer together. And so we will have again that the centers coincide. There is no change in the dipole state. We've just made them all just a little closer together. Again, we are getting no change in the center of symmetry. I mean, no change in the centers. All right. This is true for a large number of cubic crystals, though not all cubic crystals demonstrate this property of having a center of symmetry. But the cubic crystal class, a lot of them, in general, have a center of symmetry. Now we come to another example, namely a hexagonal crystal, for example. Okay? And we'll draw the hexagon very quickly. Now my drawing will probably give you a distorted picture than what you should see, but use your creative imagination. Let's say we got a positive ion, negative, positive, something, I'm sorry. And when we look at this, do we have a center of symmetry in this 2-dimensional image? No, because I can draw a vector here, the opposite direction is some other kind of ion. So we say that this 2-dimensional hexagonal figure has no center of symmetry, and that would be true in the crystal which is in 3 dimensions. So that's what we mean by non-centrosymmetric crystal. It doesn't have a center of symmetry. When you invert the crystal through some point, you will not get back the same positions. You will not get the ions in the correct positions. There is no such point in that crystal. Now in this case, when we look at the centers, no force is applied, and centers of positive and negative charges, they coincide. Okay? So there's no polarization, no net dipole moment. But now if I were to squish this by applying a force, what we see is the following. It's going to be a little distorted, but I'll... So we've got the positive charge has moved inward. The negative charge has also moved inward. And so now we've got the center of negative charge is somewhere here. The center of the positive charge is somewhere here. Because when the positive charge moved down, the negative charge is also moving up here. And so the two centers are no longer coinciding. And we are left with a net dipole moment in this direction. Now it turns out, in this particular case, when we applied the force, that the dipole moment is generated in the same direction as the applied force. But that's not always true. I apply the force this way, we've got the dipole moment along that same axis. But we can have situations where that will not be true. So in this case, because of its non-centrosymmetric nature, we will get polarization. Let me give some idea of what is called the piezoelectric coefficients briefly. When we apply the stress, I said here, along this direction, dipole moment is along the same direction. But in general, when we look, if stress is applied along a particular direction, let's call it J, some direction J, and we will call the stress Tj. Then the induced polarization, Pi, is along some direction I. They may coincide, they may not. I'm just taking a general situation. In the previous case, you had J and I are the same because it's along the same direction. But in general, it may not be the same. We can relate these two with a very simple relationship. Pi is equal to Dij Tj, where Dij are called the piezoelectric coefficients. What would we call this Dij? Have you come across that notation before? Scalar, vector, tensor, right? So it's these are tensors basically, right? So these piezoelectric coefficients, if we know them for a particular material, then if we know along which direction we are applying the stress, we can calculate along which directions we will get what kind of polarizations we will get. It turns out that if you look at the opposite effect, namely that I'm going to apply a field along I, and the strain that is induced is along J. So I put along I the electric field, and I'm looking in which direction has it changed its dimensions. It's along J direction. And here also strangely, Sj is simply Dij Ei. The same Dij is the piezoelectric coefficients give us this. So once we know the piezoelectric coefficients for a material, for that particular kind of crystal, it's very easy to then make use of it to do things for us in different directions, because I know where I have to apply the field to get change in which direction or vice versa. Another term that is useful to us is called the electromechanical coupling coefficient, electromechanical coupling factor, which has the symbol K. And as the name implies, and I told you, we can think of it as converting electrical energy to mechanical energy. We want to know how good a converter it is, one way or the other. And it is expressed as K squared is equal to the electrical energy converted to mechanical energy divided by the input electrical energy. All right? How much of the electrical energy got converted to mechanical energy is what is k squared, and so then from there you can get k. Or alternatively, for the opposite effect, you can say mechanical energy converted to electrical energy divided by input mechanical energy. It's getting a little small there, I apologize. I'll read that out. Mechanical energy converted to electrical energy divided by input mechanical energy. So these terms are useful for us also in knowing, even though it can do, how good is it in doing this? How efficient it might be, a way to understand it. Here's some quick numbers for quads. D in a particular, one of the coefficients, Dij, is 2.3 into 10 to the power minus 12 meters per volt, just by way of comparison of similar coefficients. And the K coupling coefficient is 0.1. On the other hand, for barium titanate, BaTiO3, we've got a coupling coefficient of about 0.49. So much higher efficiency in converting energy from one form to the other. And then there's something called PZT, lead zirconate titanate. Okay, something like PbTi, say 1 minus X, zirconia X O3. In this case, the D value is much higher, 480 into 10 to the power minus 12, and correspondingly the coupling coefficient is also very high. Very good conversion of one form of energy to the other. And when we are converting it like this, those are called transducers. That converts the electrical energy to mechanical energy and vice versa. We can think of some applications for this. And one might think of a way to convert using two transducers. I've got some kind of a material. I fix one of these piezoelectric transducers on one side and hook that up to an oscillator. And when we do that, when we are applying the field, an oscillating field to it, what do we see? This crystal is going to vibrate. So mechanical vibrations are set up here, and we will generate elastic waves into this solid, because that crystal is vibrating in contact with some other solid here. Okay? On the other side also, we've got a similar transducer, except that it's not, no voltage is applied across it, but instead this time it is hooked up to an oscilloscope. So here we are converting electrical energy to mechanical energy. Here those same waves, elastic waves that are transmitted through this medium, get to this point here. And because now they are applying a pressure to this crystal, they're straining it, we end up generating a signal. Basically, it generates a voltage across. So the two effects are made use of, one to convert electrical to mechanical energy, and the opposite transducer to convert mechanical energy to electrical energy. And one example very common these days is ultrasonography. You use that as a medical diagnostic tool. You use the sound waves to pass through, and you detect it with one transducer, and you see what is happening inside the person using ultrasonography. It's also made use of in materials to do what is known as non-destructive testing. If I have a material and I want to see are there cracks and things like that in it, now I can of course cut it up and see if there's any defects in it, but after I've cut it up, that material is no use to me. So I want to do that without breaking up the material, effectively almost without damaging it in any way. And so I could do something like this, put two of these transducers and pass these waves through it. when it encounters, let's say, some kind of a defect, it will scatter differently than simply passing through this material. So when it comes to a pore, a void, a crack, it will behave differently than if it's a perfect material. And so by doing this kind of testing, I can evaluate my material without ever having to break it up or damage it in any way. It's also found in microphones, where you're converting sound, which is vibrational energy, into electrical signals. Accelerometers, etc. There's another very common example. You ever seen these gas lighters that are used? You click, 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 and they work? They're just piezoelectric. You ever cut it open and see? It's fun. Find an old one. You'll find a little pellet in there. And basically the principle is so simple. You've got an action that there's a little pellet in here, let's say like a pen, and you've got something like a spring-loaded ball pen with a tip. So you load it up, kind of. The spring keeps it away. And when you click on it, it releases that spring-loaded stuff, and it goes and gives a momentary impact onto this pellet here. And that impact is your mechanical pressure. So for a brief moment, there's a deformation of the crystal, which leads to high voltage. And across two electrodes that are connected across two sides of this pellet, you get a spark. So it's a very, very simple yet elegant application of this piezoelectric effect. We'll come to the next couple of effects rather quickly in the interest of time. Ferroelectric and pyroelectric crystals. Now, some crystals have got permanent dipole moments, whether there's a field or not. We noted some of those earlier. In form of gas, we had seen HCl. But here you can actually have some crystals that have permanent dipole moment. And an example of that is, again, barium titanate, very useful material for all kinds of things. In this case, if you look at its crystal structure of barium titanate, you've got a cubic kind of structure with oxygen ions at the 8 corners here. And then you've got, barium ions, these are bariums here. Oxygens at the face centers. So all these darkly shaded ones, let's put them as barium. 2+. And then I stick in oxygens at each of the face centers. And then we've got a little titanium ion sitting in the center of all this, at the body center. That's basically the barium titanate structure in 3D. Okay? 8 of them are barium in the corners, 6 oxygens in the face centers, and 1 titanium in the body center. If you look at it in sort of a projection, what we will see is that when the temperature is above 130 degrees centigrade, it has this structure that I just showed, the cubic structure, and I'm sort of looking at it from one side, projecting everything. And in that case, we will have something that looks like this. Where now the titanium is right at the center, everything is, there's no dipole, no net dipole. This is for T greater than 130, sorry. This is the cubic structure. On the other hand, when your T is less than 130 degrees centigrade, what we will see is that everything else is the same, more or less. Except that our little titanium fellow has got displaced like this in what is a tetragonal structure. So we end up having a net dipole because now the centers of positive charge and negative charge don't coincide. So as long as you're below 130 degrees centigrade, barium titanate in the tetragonal structure has a net dipole. When you go above 130 degrees centigrade, the structure changes to a cubic phase, and then there's no net dipole. The temperature, 130 degrees centigrade, is referred to as the Curie point, or Curie temperature. Okay, and this is basically the ferroelectric. There's a net dipole moment, a permanent. That the name comes from similarity to ferromagnetism, ferroelectric, ferromagnetism. We've got permanent dipoles. And one comment I'll make here: all ferroelectrics are piezoelectrics. We can guess that because if there's a net dipole moment, if I shift it, I'll get changes there. Okay, so all ferroelectrics are piezoelectrics, but not all piezoelectrics are ferroelectrics. I'm just abbreviating piezos and ferros, but you can expand that. Okay, so this is basically ferro. There's a permanent dipole moment. Very quickly, the pyroelectric effect, as the name implies, when you have a change in temperature delta T, there will be a change in polarization corresponding to that of delta P. Heat, change in polarization. Same here, the barium titanate, I change the temperature below 130, above 130. There was a dipole moment, there's no dipole moment. Similar to that, there are many materials that where delta P will change when you change temperature. And we have the pyroelectric coefficient which is equal to dP by dt, the change in polarization for the slightest change in temperature. Examples of these are again barium titanate, which I just gave you the picture, or PZT, which has been modified in some way to demonstrate this effect, lead zirconium titanate itself. And where would you apply this? Very interesting application is in infrared detectors. Imaging. So into some view, we've got all these goggles and all you see in all these movies, the infrared people, they can see, the soldiers can see and all that kind of stuff. The detectors can be made so sensitive that a change in temperature of even some few thousandths of a degree will generate a voltage because of the change in polarization that can be detected. So very minute temperature changes, satellite imaging, when you're going across, you can see how temperatures are different to detect whether it's vegetation or what, because temperatures are different. There are all kinds of applications. So the pyroelectric effect can be made use of as very efficient infrared detectors. Okay, I didn't have time. I'm glad I skipped that part about the different materials for capacitors. I would have just told you that different kinds of materials are used for different capacitors and the kinds of capacitors that are available, but I think I'm going to skip that. But you've got polymers, you've got ceramics, you've got metals that can be used as metal oxide ceramic capacitors, but I'm not going into it. Though that was a more practical thing I could have taught, but I just don't have the time for it. If I have 3 more classes, and we'll see what we can do with those 3 lectures in the next few days. Okay.